So firstly, thanks to the organisers for giving me this spot after the previous speaker had to cancel. So the theme of my talk will be the use of single precision in 4D-Var data assimilation. Now, I can't give you a definitive answer to this question here, of course, by looking at simple models. But I do want to identify some of the key concepts that we should have in mind when we tackle this problem. And I hope to at least encourage those of you working in operational centres to keep an open mind regarding single precision and perhaps to perform some of your own tests. So first, a primer on floating point arithmetic. Floating point numbers come in three formats: double, single, and half precision. And this diagram here shows how the value of pi is encoded as a floating point number. So with double precision, we have around 15 digits of precision. And with single, we have 7, and with half, we only have 2 or 3. So the number of digits of precision that we have is determined by how many bits there are in the so-called significand. This is the light blue bits here. So in this talk, when I say reducing precision, what I'm talking about is reducing the number of bits in the significand. I won't be mentioning anything about the exponent. So when we lower precision, when we reduce precision, of course, we get a higher error in the numerical calculations, basic arithmetic operations. So for every significand bit that we remove, we double the rounding error. However, reduced precision arithmetic tends to be cheaper, especially for memory-bound applications like weather models. And this is the main motivation for looking at it in the first place. So the idea of single precision weather forecasting has become quite popular recently in various operational centres, notably ECMWF, who published this result in 2017. So they translated their entire forecasting model into single precision and found that it was about 40% cheaper than the double precision model. And you can see on this plot, it has basically the same probabilistic forecast skill as the double precision model. Now, this model at the moment is undergoing some internal testing, and the last I heard, it still has some issues with mass conservation. But it's very much on the ECMWF future roadmap for operations. So what about 4D-Var? Well, as we all know, 4D-Var is an optimization problem. So we define some objective or cost function as a function of a four-dimensional state vector distributed across an assimilation window. And we have to find the minimum of this cost function. Now, in the simplest case, without any consideration of model error, the cost function only has two terms: the background term, which represents our a priori knowledge, and the observation term, which is the sum of the squared distance to all the observations across the window weighted by the error covariance matrix. Now, we typically use a gradient-based algorithm to minimize the cost function. Now, the gradient of the background term is trivial, but the gradient of the observation term is very much not trivial because it requires linearizing the nonlinear forecasting model to give the tangent linear and the adjoint models. We require the tangent linear model to compute the innovations across the assimilation window, and we require the adjoint model to compute the gradient of later terms with respect to earlier terms in the cost function, so the gradient of the cost function. And I would like to propose that we use single precision arithmetic to lower the computational cost of these two models. And anyone who's written one of these from scratch will tell you that they'd end up being 2 or 3 times longer just in terms of lines of code. And then they end up dominating the computational costs of 4D-Var typically. So my experimental setup, I've been using the OOPS system of ECMWF. This is a new model agnostic data assimilation framework developed at the European Centre. It comes bundled with a simple quasigeostrophic 2-level beta plane model. And here's an illustration of the domain here. So you can think of it as like a simple mid-latitude weather model, basically. And I'm going to be considering not just double and single precision, but also all levels of precision in between. So I reason that any effect that we get from using single precision will be more easily identifiable if we look at all levels of precision, not just double and single. And to do that, I used a software emulator. So that's the model setup. As for the assimilation setup, it's a standard OSSI, so I'm using a perfect model assumption. I have a truth, and I derive observations of stream function and wind from that truth. And I'm going to be looking at a well-conditioned problem and an ill-conditioned problem. And the parameter that determines the conditioning is the level of observation error. So I've got this is the well-conditioned problem. So it has a relatively high observation error, and I also have an ill-conditioned problem, which has a relatively low observation error. And I'm going to be looking at standard incremental strong constraint 4D-Var. So there's no consideration of model error yet. And I'm going to be using a conjugate gradient minimizer, and the reason I mentioned this detail will become clear in a few slides' time. So let's begin with the tangent linear and adjoint model identity. So the tangent linear and adjoint models are related by this expression here, where x and y are arbitrary vectors. Now, if we had a perfect infinite precision computer, then this identity would be satisfied exactly. But because we're using imperfect finite precision floating point arithmetic, there will in fact be a small difference between the left-hand side and the right-hand side. So this plot here shows the relative error on the red curve between the left-hand side and the right-hand side. And on the x-axis, we have the level of precision. So we have high precision on the right and low precision on the left. And I've marked out double, single, and half there. And you can see that the difference goes up as we lower precision, almost exactly with the machine epsilon, actually. So in other words, when we lower precision in the tangent linear and the adjoint models, we increase the asymmetry between those two. And we might expect this to have some deleterious effects on the minimization process. So let's look now at the assimilation experiments. On the left, I have the result from the well-conditioned problem, and on the right, I have the ill-conditioned problem. On the y-axis, again, I have precision, so I've got high precision at the top and low precision at the bottom. I've marked out double, single, and half there. And each row on this diagram is it visualizes the minimization process of 4D-Var. So the color is the value of the cost function at that particular iteration. And you can see going from left to right, we're proceeding through the minimization. So it starts on the left and finishes on the right. And for the well-conditioned problem, as you can see, we can basically use any level of precision without any degradation in the assimilation. This is a very easy problem to solve. However, for the ill-conditioned problem, we require more and more iterations as we go down in precision. Specifically, we need around 25% more iterations for single precision versus double precision. So even though the single precision model runs faster, it takes longer to reach the minimum, the solution, which is not good. So why does, when we lower precision, why do we need more iterations? Well, as I said, I'm using a conjugate gradient, specifically preconditioned conjugate gradient minimizer. The way this works is it constructs a chain of vectors starting from the initial guess and finishing, hopefully, at the global minimum. And at each step in the iteration, we must compute the residual, which happens to be the negative of the cost function gradient. Now, in order for CG, conjugate gradients, to converge efficiently, the residuals at subsequent steps must be orthogonal, and they would be orthogonal if we were using perfect infinite precision. However, because we're using floating point arithmetic, there will actually be a slight non-orthogonality to these residuals. And I've tried to illustrate this here. So the solid line would be if we had infinite precision, and the dashed line is for this reduced precision. You can see that the step direction is slightly wonky. It's in the wrong direction. And so with perfect precision, we would get to the minimum in 2 steps. But when we use reduced precision, we slightly miss the minimum, and we take a couple more iterations to get there. However, there's quite a standard, simple fix to this problem, and that is to reorthogonalize the residuals at each step. So we keep track of all the previous residuals, and when we compute the next one, we subtract their projection from the previous residuals every time. So we basically use Gram-Schmidt to keep them all in line. So if we go back to the previous experiments only with reorthogonalization, you can see that although the well-conditioned case hasn't really changed, the ill-conditioned case is vastly improved, and we can go even well below single precision without affecting the minimization of 4D-Var. Now, reorthogonalization is certainly not new. I certainly didn't invent it myself. And in fact, it has around a 50-year history in Krylov subspace methods, specifically for the Langchos algorithm for computing eigenvalues. And in fact, it's actually switched on by default in OOPS. So I'm not even proposing that we introduce something new. I'm merely suggesting that the techniques that we're already using provide a kind of level of tolerance to lowering precision. So I'm going to conclude there with a couple of points. So reducing precision in the tangent and the adjoint models introduces asymmetries between the two, which affects the minimization for the ill-conditioned cases, as I just said. However, the minimization is tolerant to quite significant perturbations to the gradient vector, just as long as we reorthogonalize our residuals. So thanks for listening.